Okay, in this presentation, we'll do an example problem using the Gibbs equation, the delta G equals delta H minus T delta S. Let's consider the reaction where hydrogen sulfide gas reacts with oxygen gas to give water, and this water is going to end up in a liquid form, and sulfur dioxide gas, right? So in order to use our equation, we need to find our standard heat of reaction and our standard change in entropy for the reaction, right? And remember a couple of things, right? The 0 here means we are under standard conditions, right? So standard conditions for thermodynamics are 25 degrees Celsius. Any gases are at 1 atmosphere. Any solutes are in 1 molar. And any liquids or solids are pure, right? So that's what the standard conditions means. We're under those conditions for each thing, right? And so we can use Hess's law to determine the standard enthalpy change. So delta H0 for our reaction is going to be equal to the sum of N times the heats of formation for the products minus the sum of N times the heats of formation of the reactants, right? We always go product minus reactants, right? And so that's going to equal, and I'm going to give myself a little more room, right? If we go products, it's going to be 2 moles times 285.83 kilojoules per mole, right? That's the water, plus 2 moles times the negative 296.83 kilojoules per mole, right? So there's my products minus 2 moles. Let's get a little repetitive. Oh, and these are negative. I missed my negative sign there. Minus 20.63 kilojoules per mole. Plus 3 moles. But since it is an element, it's 0 kilojoules per mole, right? The heat of formation for elements is 0. Right? There. I think I'm missing a bracket there. And so when I add that all up, I get negative 1,124.06 kilojoules, which then we can go back and normalize to any one of the reactants if we want to get back to kilojoules per mole. Okay, so that's our delta H0 for our reaction. Just like we could use Hess's law on enthalpy, we can always also use the Hess's law principle on entropy. Entropy is also a state function, and so it follows those same state function rules. So we can find our delta S 0 for our reaction in that same way, right? And so that is going to equal, right, the sum of N times the S0 for the products minus the sum of N times the S0 for the reactants. And so that would equal, right, for water, 2 moles times 69.91 joules per mole Kelvin, right? Plus 2 moles, right, for sulfur dioxide times 248.22, and that's in joules per mole Kelvin, minus, right, now we go to hydrogen sulfide, 2 moles times its entropy is 205.79 joules per mole Kelvin, plus 3 moles times 205.138 joules per mole Kelvin, right? And so if we add that up, we get negative 390.734 joules per Kelvin, right? Now, if we look at this, right, we've got our results here. We have a negative delta H, right? That's favorable. But we also have a negative delta S. That is unfavorable. Right? So our first question is going to be, at standard conditions, which one wins? Okay, so now at standard conditions, we said standard conditions were 25 degrees Celsius or 298.15 Kelvin, right? We have to work in Kelvin. And so we can find, right, that our delta G for our reaction under standard conditions is going to be our delta H for our reaction under standard conditions minus the temperature in Kelvin times the delta S for the reaction under standard conditions. Now, one thing we have to note here, right? Delta H is given in kilojoules here. Delta S is given in joules per Kelvin. We're doing subtraction here, which means this number and this number have to be in exactly the same units. So you have to decide, are you going to work in kilojoules or are you going to work in joules? And I will tell you, right, in this case, I think it will be easier to work in joules. Okay? So we have to make our conversions. So that's going to be equal to negative 1,124.06 kilojoules minus our temperature is 298.15 Kelvin times negative 0.390734 joules per Kelvin, right? This number converted to kilojoules, kilojoules per Kelvin, right? And if we do that math, we get negative 1,124.06 kilojoules plus, right, minus times minus would give us plus 116.50 kilojoules, because kelvins and kelvins cancel, which gives us an answer of. So here we've brought forward our information, but now we have to think about this, right? We know if delta G is negative, our process is favorable. If delta G is positive, our process is unfavorable. Well, what's between positive and negative is 0, right? 0 is the transition. So what we want to ask ourselves is, at what temperature will delta G for the reaction equals 0? Because that will be the transition between favorable and unfavorable. So we can set up our equation, right? Right, we've got our delta G 0, or our delta G for our reaction. In this case, we're going to use our delta H 0 for the reaction as an estimate at any temperature because it doesn't change much with temperature, minus temperature. That's what we're going to find. And the same thing is true of delta S0 for the reaction. It doesn't change much with temperature. So we can use these two numbers that we determined for 25 degrees as an estimate for other temperatures. Okay? So all we have to do is substitute in, right? We're going to put 0 here. We're going to put our negative 1,124.06 in here, and that's kilojoules, minus temperature, which we don't know, times our 0.39. Oh, I think we can probably get away with leaving it at 391, right? Kilojoules per K at this point. Okay? Now all we have to do is do the calculation. Before we get away here, we have to remember that's negative there, right? Otherwise it won't work at all. Right? So here's our equation, right? All we have to do is work it out. If we add the enthalpy, we get plus 1,124.06 equals minus times minus gives us plus temperature times 0.390734 kilojoules per Kelvin. This is going to be a big number, right? So we're going to have our, and this is kilojoules, so our plus 11,024.06 kilojoules divided by 0.390734 kilojoules per Kelvin. That would give us a temperature in Kelvin, which would be 2,877 Kelvin, or 2,604 degrees Celsius, right? So at that temperature, right, above that temperature, the reaction would become unfavorable as a result of the greater effect of entropy at high temperature. Now, obviously, our liquid water couldn't exist at this temperature, but you get the idea of how we can find a transition temperature for a reaction where enthalpy and entropy disagree. There is a temperature transition, right, above which it is either favorable or unfavorable, and below which it switches. Okay? And you should be able to find that temperature transition. Okay? The other thing we can do is just estimate, right? Estimate the delta G at another temperature, right? Using temperatures, putting in temperature, finding delta G. Okay? So those are the major kinds of problems we're going to do with the Gibbs equation. That is the delta G equals delta H minus T delta S.